we have to study the Doppler effect. So describe what is meant by the Doppler effect. This is when there's a change in pitch which is heard by the observer or the detector when 1. The source of the sound is moving relative to the medium and the observer, or the observer is moving relative to the medium and the source, or a combination of the three. Most cases that you experience, the source of the sound is moving relative to the medium. There's a shift in the observed frequency which depends on the speed concerned, either the speed of the observer or the speed of the emitter. This is a nice graphic which shows this in a nice way. Here we have an ambulance moving towards the observer. Notice that the wave fronts get bunched together before the ambulance, so the observer observes them at a high frequency, and that the wave fronts get spaced out when the source is moving away from the observer and you observe a low frequency. We'll observe that again, and with each wavefront I will demonstrate by clicking my fingers. So observe the frequency when it approaches and when it recedes. On recession, there's a much lower frequency observed by the observer. If the source is moving relative to the observer, what do we notice? That the same sound is radiating sound waves at a constant frequency in the same medium. However, the observer observes a frequency which is higher if they are to the right or they're in front of the source. One way of looking at it is that the center of each new wavefront is now slightly displaced to the right when it is caused. So effectively the waves get bunched up, the wavelengths get shorter, and the frequency is higher. If you observe from the other side, you notice that the wavelengths are spread out, the wavelength is longer, and the frequency is lower. Here we see the same thing again. In front of the source, the wavelengths are bunched together. Behind the source, they're spaced out. If we take this, where the source is moving at the same speed of the wave, the wavelengths get basically crushed together, so you don't hear the source until it is level with the observer. So what does the observer detect? Nothing until they are level with the source. And they will basically experience a pressure wave, and therefore a big bang effect will be caused. So you get this crashing through the sound barrier is basically because you hit this wall of high pressure which is caused by the movement of the object. If you have a speed which is faster than the speed of sound, you will get an effect like this, where the sound is left behind and you will not hear the sound until the object has passed. Now we need to apply the Doppler effect equations for sound. remember this one here. We have a moving source. We use this equation. The observed frequency for f prime is equal to the frequency of the source. V is the velocity of the sound, and we have v plus or minus us, which is the velocity of the source. Now you have to decide which one of these you need to do. You have to remember that this term will be you use a negative if it's approaching and use positive when it's receding. So effectively, when it's approaching, you will divide by a smaller number. The quotient will give a higher value, and therefore they will observe a high frequency. You can do an example here. A car travels at 30 meters a second and emits a frequency of 200 hertz. The speed of sound is 330 meters per second. What frequency is perceived by an observer before and after it passes? And then you can try the same for a jet, which travels at 260 meters a second. The answer you should find is this one. F1 is when it's approaching at 30 meters a second. The observed frequency will not be 200, it will be 220. When it recedes, the pitch will drop to 183. On the other hand, if you have a jet, as it approaches, it will be a frequency of 940, and when it recedes, it will be 112 hertz. Here we have another example where the observer is moving relative to the source, and we use this equation. F prime is equal to F v plus or minus nu naught v. In this case, when they're approaching, we add the velocities. When you are receding from the source, you subtract the velocities. So try this. The observer is travelling at 30 meters a second relative to the source. This stationary source emits a frequency of 200 hertz. The speed of sound is 330, and you should find the observed frequency as measured by the observer on approach and recession. And try if they move at 260 meters a second instead. And you can also try if they travel at the speed of sound. What answer would that give? The answers that I calculated would be that the first frequency, when you approach, the frequency you would observe is 218. On recession, it would be 182. When you move much faster, at 260 meters a second, the approach frequency would be 358. The recession frequency would be 42.4 hertz. Solve problems on the Doppler effect for electromagnetic waves using the approximation delta F is equal to F V divided by C. This equation only works as long as V is much smaller than C. We could try with these examples. Let's say the frequency of emission is 890 megahertz. The approach velocity is 100 meters a second. And you should find that the shift in frequency will be 297 hertz. Example in which the Doppler effect is used to measure speed. Police cars use radar or microwaves, radio waves, to send out a frequency to a car, and then because of the speed of the car, the car receives the frequency at a slightly shifted frequency, and then it gets reflected, so we get a double shift in frequency, which is measured by the policeman.